Okay, so hello, my name is Evan, and today I'm going to explain some question about convolution in signal and system. So in here, there's actually three questions, and the first question we are asked about the convolution of a system with the piecewise function e to the power of negative t, and there's also another signal with this graph. So I'm gonna explain my uh, answer. And so here we have the original system, this one. And first, we can see here that we need to do some operation. Yeah. Here's an example of how to do it. Yeah. So let's say we have this function, and we need to we can call it ht. We need to convert it into ht min tau. Yes, and so first of all, I need to convert this e to the power of minus t into e to the power of tau min t, and it's actually just an operation of flip, but we also need to change some of like from zero, like this is zero, and change into t, and this is because in e to the power of t min tau. It's a function of tau. So if tau equals to t, then it's e to the power of t minus t. So it's equal to e to the power of 0. And that's equal to 1. So yeah, it's the same as when this function have the value of t equals to 0. So that's why in here this is 0 and in here it's t. That's because of this. But otherwise, visually, it's just flip the graph. And this is the second function. We don't actually need to do anything. So there's something that we need to do. First of all, we need to split the operation into some cases. And here we can see that I split it into many cases. So first of all, in case one, we have the case where this function is trying to enter the signal. So here this happens during t minus 1 until 0. So this point is y equals to 1. And when it started to collide with the system, uh, we can count the summation by using integral. Yeah. So during this case, it's just a normal integral, yeah, of e to the power of tau min t from negative 1. And notice how the upper limit is t, because even though t is from negative 1 to 0, but in this example of the visual representation, it doesn't actually reach 0. So it's actually reach a certain point, and we can call that point equals to t. And we just do normal integration and get this value. And next is the second case. In here, we can see that the value of t is from 0 to 1. So at this point, we know that it already have passed the block where this the signal is equals to 1. Now during 0 to 1, the signal value is equals to 2. Yeah, and so there's a little bit of difference here. So the integral must be split, because on this section from t from minus 1 to 0, the value of the signal is 1, but from 0 to 1, the value of the signal is 2. And if we want to sum it, we can use integral, but we need to split the integral. So for 0 to negative, from negative 1 to 0, we just integral it normally, and don't forget to times with the value of xt. Yeah, I forgot to mention before, but we need to times it because That's the how the function of convolution work. Yeah, this is the function. So we need to time xt with ht min tau. Okay, so on the case 2, when t is 0 to 1, here the value is 2. So on the second integral, we need to times it by 2, yeah, because the value of xt is equals to 2. And don't forget the upper limit of the integral must be equals to t, because this is the right limit is between 0 to 1, and it's in a certain point, so it could be 0, 1 or 0 0.5 or other, so we can symbolize it as t. And we just know normal integration and get this value. Next is the third case, is where it reaches maximum peak. Yeah, it's in the middle. Okay, so case 1, case 2 is automatically happen in this case, so we can just write the integral. So this is the same as case 1, this is the same as case 2, but remember to change the t into 1, because at case 3 the signal that collide will certainly pass this section. So we only need to determine the third part, which is from t from 1 to 2, because on that part the value is equals to 4. Yeah, and all we need to do is times 4, and we just need to change the upper limit to t, and don't forget to change the below limit into 1, because we want to count it when xt is equals to 4. And the other case is similar to the previous one. We just need to split the integral and add the left limit and the right limit, and don't forget to times with xt. So in this case it's 2, because for t from 2 to 3 it's equals to 2, and the same as case 5. Yeah, from t equals to 3 to 4 it's times with 1. Yeah. And don't forget another case is when t is greater than 4. Yeah, we need to add another one, which is from we just changed the integral of the last section. So in here the upper limit is t, but in here the upper limit is 4, because we can guarantee that the system will collide from the this section. There's actually another section. We can say it's case 0. It's when the signal of ht min tau doesn't collide at all with the signal of xt. This happens when the time or the t value is less than -1. And I don't write it here because it results in 0, because the signal doesn't collide at all. So we can just forget about that case. And all we need to do is to summarize all the integrals into one piecewise function. Yeah. And here we got the value of the system, the convolution system of xt and ht. Yeah, I notice in here it's 0, it's for case 0, where both the signal doesn't collide, and the rest I already write it down here. So the Matlab code, as you can see, this is just like the normal time. So in here, I registered the time from -2 to 6. So in here, the graph is actually from -1 to 4 only, but for better visual representation, I add more space. And 0.01 just tells like the uh, how much like the space between it. Oh yeah, so this is the piecewise function. As you can see, how to rate it is like t from -1 to 0, it's the value is 1. Yeah. So from t to 0 to 1, the value is 2, and so on. So this is the xt, and this is the convolution function, and below is the plotting function, and here is the result. Yeah, so this xt, this ht, yeah, the ht is still normal, we haven't flipped it yet, and this is the convolution result. This function should be a graphical representation of this function. Okay, next to question number 2, you've got the convolution of this signal. Yeah. First of all, we can, because this is the HT signal, we can convert it to HT min tau. And we got this value and this graph. And all we need to do is do the same thing. So for case 1, it happens when t is from -1 to 0. We just do normal integration. Yeah, the bottom limit is -1 and the upper limit is t, because during this period only this section that I underlined collides. So the left, the most right is t, not 0. And also there might be a case 0 where t is below 0, but that will always result in 0 because both the signal doesn't collide. Okay, next case is case 2. This happens when we can say the triangle is inside the rectangle. So it happens when t is from 0 to 1. So yeah, if just now it's from -1 to 0, so now t is from 0 to 1. And here it's a bit different. The bottom limit is from t minus 1, while the upper limit is t. You can say that because uh, the value of the left and right limit is always changing. It's not constant. So yeah, we need to represent it using variable t. And by normal integration, we get this value. And so on with case 3, it's just the same, except the upper limit is 1 because the signal only collides until value 1, so it's a constant. While the left is t minus 1 because the value always changes. And by normal integration, we get this value. Okay, by summarizing everything, we should get this value. There's also another case where t is above 0 is equals AMG above value 2 is equal to 0, because after t is, if the value of t is more than 2, both the signal doesn't collide anymore. This is different from question number 1. Yeah, in here 0 only one time, while just now 0 happened twice. Yeah, because the xt in the first question is the value can go to unlimited, like different from this xt where it goes 0 above 1. So yeah, that's the difference. Maybe to better understand it, if we look at this graph, it can go to negative infinity and might have a value but very small. Yeah, but it reached 0 but still have value very small, but it is not certainly 0, where during uh, this example question, xt is equals to 0 when t is a very high or very low number. So yeah, this explains why 0 happens here. And this is the Matlab code. It's similar to before. I set the a graph value from -3 to 3 with a spacing of 0.01. This is the piecewise function of xt, and this is the piecewise function of ht, and I just convolution it and plot it. So this is the result. This is xt. As you can see, it's the same. This is ht, and this is the convolution result. Okay, now for number 3, it's this question. Okay, so we have xt as normal rectangular and ht with triangular shape. We just do normal flipping and change the function to ht min tau, and we get this function. And then we just do the same thing as before, where case 1 is t from -2 to -1. We get the integral with the limit from -1 to t plus 1. And this is the integral result for case 2. Uh, the t value is from -1 to 0, uh, and we can see the limit is from uh, t to t plus 1. And it is split because this is only for the right side of the triangle, yeah, while the left side of the triangle is from -1 to t. So in here the constant is always -1, while the rest is changing values. That's why it's represented using t. And normal integration, we get this value. And the rest, case 3, is t from 0 to 1. And yeah, normal integration, in here the constant is 1. So this is the upper limit, 1. Because after 1, it doesn't collide anymore. Then that's for the right side. For the left side, it's still a changing value. That's why it's represented using t and t minus 1. And another case is where only the left side is still in the rectangle, and this is the integration, and this is the function result. So the Matlab code is also similar, where first I define the time variable, then I define the piecewise function of xt, piecewise function of ht, do the convolution, and plot it, and this is the graphical result. Yeah, so this is xt, ht, and the convolution signal. So that's about it, and thank you for watching.